Good evening, everyone. On the behalf of Department of Mathematics, Wilson College Autonomous Mumbai, I welcome you all in the today's session. Our today's guest is Gaurav Sawant sir. He is an assistant professor at Department of Mathematics, Veermata Jijabai Technological Institute, that is VJTI Mumbai. He will deal with the topic of ordinary differential equations today. Over to you, sir.
Okay, thank you, Prathamesh, sir. In the previous session, the third session, we had essentially covered up to second order differential equations with constant coefficients, and we had just kept ourselves with the homogeneous equations case. So today we will see how we can deal when you have some inhomogeneous part associated with the equations. So let me share my screen. Yes, I hope my screen is visible to everyone.
Yes, sir.
Yeah. Yeah. Okay. So let me just align a few windows so that yeah. Okay. So we are talking about second order differential equations. So in the standardized form, they will typically look like y double dash plus px y dash plus qx y equal to rx. So we intend to have linear differential equations, which just means that the coefficients appearing are functions of at most x. So the y is not involved in p, q as well as r. Okay, so this is the typical equation. So obviously, when uh, Rx is identically equal to 0, we call these homogeneous equations. And when it is not identically equal to 0, it is a reasonable enough function. It is non-homogeneous. Okay. This is first thing. Second thing is that if Px, Qx are constant, then we have seen in yesterday's session that these kind of equations can easily can be solved quite easily while being homogeneous. So this I will just write DECC, differential equations with constant coefficients. So we have seen the homogeneous equations of the constant coefficients type, how to solve them. You just construct the auxiliary polynomial, find its roots, and depending on whether they are repeating, non-repeating, or if there is a complex pair, accordingly, you will have a certain form of the solution. Now, while this particular equation, which I'm going to just call by star, so uh, okay, what did I want to say? Okay, so there are typically at least three different methods to deal with the inhomogeneous cases. So each of them involves the following. So for if Rx is not equal to 0, identically not equal to 0, uh, we need to find a particular solution. We will call that particular solution as yp of x to star. And if YH is a general solution of the associated homogeneous equation of y double dash plus px y dash plus qxy equal to 0, then YH plus YP is a general solution of the equation that we want to talk about. Okay. So finding like the general solution for the associated homogeneous equation is fairly straightforward. Finding particular solution is slightly tricky. So, of course, the like super easy way to look for a particular solution is just by making a wild guess substitution, but that may not always work. So we need to have proper methods. So at the moment, let me assume that Px and Qx are still constants. We will later on mention how to deal with non-constant P. Okay, so we'll just talk about this. So for this part, assume Px is identically equal to some small p, Qx is identically equal to small q, are constants. So there are essentially two methods which help us try to find a solution of this, the equation. So our equation is y double x plus py plus q equal to rx. And let y1, y2 be two solution of the associated homogeneous equation. So the associated homogeneous equation, I'm going to just use a double star here. Okay. So we will see the method of variation of parameters. Okay. We use a different star. Okay. So what this method does is that it assumes that a particular solution for this particular this equation that has been mentioned here uh, has the form. So let uh, so we seek a particular solution of the form yp equal to uh, v1 y1 plus v2 y2, where v1 x v2 x are some functions of x. So our idea is that this yp must satisfy the above equation y double dash plus py plus q equal to rx. Okay. So there is a certain uh, intricate method of how we get about this. But for the time being, let me just provide you with the exact formula for V1 as well as V2. We can obviously work this out completely, but Of course, in the exam setting, you wouldn't have time for that. You really want to quickly find a solution. So the way it works is okay. So I will add the page later. So what we know is that uh, let me just make a little correction here to independent solution, linearly independent solutions of this. So if we have independent solutions, then I know that the Wronskian corresponding to those solutions is another non-zero function. So there are a few steps. So step one is compute the Wronskian y1, y2, just the determinant y1, y2, y1 dash, y2 dash. Okay. So if these y1 and y2 are linearly independent, then this Wronskian is always going to be either entirely zero or like entirely zero won't happen for linear independence. Though, so the only other case is it is not equal to zero at all. Anyway, so we have this. Okay, there is a non-zero Wronskian, and once that happens, we calculate V1 and V2 using the following formulas. So V1 equal to uh, integral minus integral y2 r divided by wy1 y2 dx, and v2 similarly is plus integral y1 rx wy1 y2 divided by wy1 y2 dx. Okay, and once you have that, then you get the particular solution as yp equal to minus y1 integral y2 rx dx over w y1 y2 plus y2 integral y1 rx wy1 y2 dx. So in this entire procedure, we are expected to suppress all the constants of integration because we are finding this particular solution that those specific constants of integration are already kind of taken care by the solution of the associated homogeneous equation. That expression, the associated homogeneous equation is going to have a solution of the form C1 e power R1x plus C2 e power R2x or for non-repeating case, and C1 plus C2x whole times e power Rx in case of a repeated root. So those C1 and C2, those constants are already taking care of that particular constant of integration. So for the particular solution, we need not worry about that. All right. So is the formula understood for everyone?
Yes, sir.
Yes, sir.
Yeah. Yeah. So let us see this formula in action by looking at a particular question. So let me just get the question up. Okay. So we have y double dash minus 2y dash plus y is equal to e power x. Okay. So this e power x is my Rx. Okay. So if we look at the associated homogeneous equation, uh, that is associated homogeneous d. So this is y double dash minus 2y dash plus y equal to 0, which you can easily see that the auxiliary polynomial has uh, r equal to 1 as the repeating root, and therefore a homogeneous solution is going to be of the form c1 plus c2x times that r equal to 1 is the repeating root, so e power x. Okay. But now you see that you have Rx equal to e power x, and we have to make sense of these. So first thing, forget about the constants. I have the functions y1 is equal to e power x, y2 equal to x e power x. These are my linearly independent solutions for the homogeneous part. Okay, we calculate their Wronskian. So if we do that, ex x e power x, e power x, and here what we will have x e power x plus e power x. So x plus 1 e power x. And when we calculate that, we will end up with just e power x as the answer. E power 2x as the answer. So e power x times x plus 1 e power x. So x plus 1 e power 2x minus x e power 2x. So that x cancel out and we are left with that 1 times e power 2x. So that survives. All right. And therefore, we will just find the particular solution. Let me write the full formula equal to minus y2 integral, uh, not minus y2, right? Y1 first. Uh, Minus e power x minus y1 integral y2 Rx dx divided by the Wronskian plus y2 integral y1 Rx dx over the Wronskian. Okay, this now is pretty straightforward. So all the e power x is in the numerator and e power 2x in the denominator cancel each other. And then we are left with minus e power x integral x dx plus x e power x integral 1 dx. This just ends up being equal to, uh, so x e power x becomes x square e power x, and minus e power x integral x becomes minus e power x times x square by 2. So x, there is a minus x square by 2 and then there is a plus x square that gives you uh, x square by 2 e power x. Correct? And therefore, the general solution is y equal to yx plus yp, which turns out to be c1 plus c2x plus x square by 2 e power x. All right. Now it's just a matter of putting the given initial conditions to find out exactly what y is and then put y x equal to 1 to get the value for y1. Let's do that. So y0 is equal to 0, which corresponds to c1 equal to 0. So we are done with this. Y dash of 0, is it y dash? Yeah, y dash is 0 is equal to minus half. So let's calculate y dash from this expression. So I will have c1 plus c2x plus x square by 2. There is an e power x, but I'm going to take it out common anyway. So the first expression, then the derivative of the second, plus derivative of the first and then second. So that e power x is coming out common, plus the derivative here is c2 plus x. The e power 0 will e power x. So this is my y dash, and so this entire expression on the left hand side, that is equal to y dash. So I put x equal to 0, and I should get minus half equal to c1 is already 0, it will go away. I have c2 plus uh, okay. So the other terms are just kind of going away. The x terms are going away. X square by 2 is going away. C1 is 0. We are left with C2. So C2 is minus half. Okay, that is it. So exact solution is y is equal to C1 is 0. C2 is minus half minus x by 2 plus x square by 2 whole times e power x, and therefore y1 is equal to minus half plus half e power 1. That is just all right.
Yes, sir.
So this turned out to be pretty interesting, straightforward problem.
Sir, I have a question. All
Yeah.
things are okay,
Hmm.
algorithmically okay, but you have chosen e to the power x for particular function y1
Hmm.
and y2
Hmm.
in the such form e to the power x and x e to the power x. But how
Yes.
can I guess for such thing in different problem?
See, different problems that will come from this. So, for instance, this particular problem had the auxiliary equation having a repeated root. Whenever
Yeah.
there is a repeated root, I'm going to have to do that e power rx and x times e power rx. Otherwise, you are not going to get linearly independent solutions.
Yes. And
Okay.
there are no particular way of thinking or guessing what will be the possible values of y1 or y2.
Uh,
If in
yeah.
case Rx would, if I would take Rx as a sin x, suppose,
Hmm.
then the choice of y1 and y2 will be different.
Not really. So, see, the y1 and y2 are already provided to you by the auxiliary equation.
Yeah.
So
Okay.
what happens is that, like depending on the form of Rx, like that particular guesswork actually is coming in the method of undetermined coefficients, where you would essentially just look at the inhomogeneous path, then guess a particular solution accordingly, and have certain constants hanging about or undetermined coefficients hanging about, and then you see whether the equation is satisfied by passing it through the differential equation. So that will work only if you have those suitable forms. But this method, variation of parameters, is quite general. Whatever your R is, it is going to work.
Okay. Okay, sir.
Yeah. So let's go for, since you did ask about sin x, let's see a question involving sin x. Okay. So let me just get that question up for you all. So now this one is an MCQ question. Okay. So my Rx is equal to sin x. This time there are certain values of A already asked in the question. So let's see what happens in those cases. Okay. So first thing, if A is equal to 0, I have y double dash plus y equal to sin x, and the corresponding homogeneous solution yh is equal to. So I have the root for auxiliary polynomial as plus or minus I, and therefore my general solution will have some constant times sin x plus another constant times cos x.
Yes, sir.
So c1 sin x plus c2 cos x. Okay. So if you are going to look for a solution using undetermined coefficient, you would perhaps, because this sign is already appearing here, you would perhaps guess a solution of x sin x plus sin x plus cos x, like that, and then you would put it in. But otherwise also it is not that big a deal. Let's see. So first of all, we have this homogeneous solution. So y1 is equal to sin x, y2 equal to cos x. Uh, then my w is uh, sin x, cos x, cos x minus sin x equal to minus 1. And then correspondingly, uh, y particular is going to be minus y1 integral y2 y1 divided by w dx plus y1 y2 cos x integral. Then I have y1 inside over minus 1 dx. Okay. Now tell me what that comes out as. So there is this minus sign will get cancelled, sin x. Inside there is cos x sin x. So that is half sin 2x, right?
Yes, sir.
Dx and plus uh, cos x, uh, and then there is a sin square x minus cos x. So what does sin square x convert to?
1 minus
2,
2 cos 2x.
yeah, 2 minus cos
Uh,
2x, right?
yeah.
2x dx. Okay, and now dealing with them is straightforward. We get, so here I have sin 2x by 2 dx. So I will get minus cos 2x by 4.
Yes.
The sin square x is equal to 1 minus cos 2x by 2, na?
Yes, sir.
1 1 minus cos
Uh,
2x.
Upon
cos
2.
cos
Is
x by
equal
half.
to sin square x. So we
Okay.
need
Upon
to
Yeah,
divide
yeah,
it by
sure.
2.
Yeah.
Sure, sure. So we have 1 minus cos 2x by 2. So our first one has become minus 1 by 4 sin x cos 2x. And then the next one is what? The cos x. There is an x by 2 and minus I will have 1 by 4 sin 2x.
Yes, sir.
Okay. Now just combine this together. What we get is 1 by 4 mm, sin x cos 2x minus cos x uh, sin 2x cos x minus cos 2x sin x, and then there is a x by 2 cos x. Okay.
In the first thing, it is a formula of sin 2x minus x, that is mean sin x in the whole
Yeah, yeah,
expression of
yeah,
parenthesis.
yeah. This will get converted. I am going to leave that there. The reason is that I am looking at the option, right? The
Yeah,
option says what happens in the case A equal to 0. It is saying that all solutions are unbounded over R.
yeah,
Okay.
because
Huh.
of x here.
So there is that x over 2 times cos x. So this x is helping it go unbounded.
Yes.
So we have essentially got our solution already.
Mhm.
Okay.
Uh, from that the fact is now quite clear that have to guess what is my form of yn, the general
YH.
uh, YH, sorry, corresponding homogeneous solution. Uh,
Hmm.
Viewing that, we can assume the what will be the possible values of those uh, y1 and v1 and v2.
Yes. So V1 and V2 are given explicitly by certain formulas. So,
Hmm.
and those formulas only involve the two linearly independent solutions Y1 and Y2 of the associated homogeneous equation.
Yes, and
Of course.
one
Yeah, yeah.
one things here, when finding out the YP particular, those
Hmm.
are here we are meeting the constant term which are usually add after integration, because of this is uh, two integration, and they are cancelling among themselves after
So
performing this integration.
not necessarily. So what is happening is that those constants of integrations which will appear here
Yeah.
outside, they have the solutions of the associated homogeneous equation, right?
Yes, sir.
Okay. So let
Okay.
me just write it in blue somewhere. So what happens when you use some constants of integration here?
Yes, sir.
Okay, so if I have yp equal to it is minus y1 integral y2 r dx over w, and then plus y2 integration y1 r dx over w, right? So if I happen to use some constants of integration inside, so I would have minus y1, then I will just write answer 1 plus maybe k1. So whatever the result of the integration that I have just put as answer 1 for the time being, and then plus y2, the result of the second integration, plus some constant of integration. And if I open it up, I would get minus y1 first integration plus y2 second integration So this part is what essentially we did here before in the question, in solving the question. And then you are left with uh, this term minus k1 y1 plus k2 y2. Okay. But then the second bracket is essentially a solution of the associated homogeneous equation, because y1
Yes,
and
yes,
y2
yes,
are
yes.
linearly independent solutions, and this
Yes,
k1
sir.
and k2 are just constant. So this bracketed term is again a solution of the homogeneous equation. So
And
that,
get consumed in the general solution part.
yes, so that will get consumed in the homogeneous solution that is already inside YH.
Okay.
So that is why we absolutely don't need to worry about that appearing in the particular solution. All right, that solves your query.
Yes, sir, clearly.
Yeah, yeah. So, like a mini exercise for everyone is that this being an MCQ question, only one of the answers was correct. But just for practice, you could just try to find particular solution for the case a equal to 1 as well as a equal to 2. So you just have to use the same methodology, find the solution for associated homogeneous equation that will give you linearly independent y1 and y2, and then you use the formula to find the particular solution for uh, that particular case, minus y1 integral y2 rx over dx over w plus y2 integral y1 rx dx over w. And then once you have that, you add that particular solution to the homogeneous equation to get the full general solution. And in case there were the certain initial conditions are given, you put those to find out the values of C1 and C2, and therefore getting the like full answer. And then answer the whichever specific question is asked. So turns out to be a fairly straightforward affair to everyone.
Yes, sir.
Okay. Now let me think of another question, which should be fun. So, this. So let's look at yet another type of uh, question, yet another like language of question, which looks scary, but it is not. Okay, so let me take this. So you have e power x, all right, and our differential equation is y double dash plus 3y dash plus 2y on the left hand side. Okay, so let me just write this x, and uh, since the associated homogeneous equation has the auxiliary polynomial r square plus 3r plus 2 equal to 0, its roots are r equal to minus 1 and r equal to minus 2. Therefore, my homogeneous solution is yh equal to c1 e power minus x plus c2 e power minus 2x, with y1 equal to e power minus x, y2 equal to e power minus 2x. Correspondingly, my w is e power minus x, e power minus 2x, minus e power minus x, minus 2 e power minus 2x. And that turns out to be minus 2 plus 1. So minus e power minus 3x. Then yt. So whenever you see particular integral or integral curve or particular solution, all of these things mean the same thing. Okay. So essentially we want to really find out what yp is. Okay. So this yp is minus y1 integral y2 rx dx divided by w plus y2 e power minus 2x integral y1 e power x dx over minus e power minus 3. So now the thing is that there are several negative signs, several exponential. So the thing that works is just to keep calm and don't get flustered by these. So we have e power minus x. Inside there is a minus 2x, above there is a minus 3x below. So on cancellation, I will get e power minus x below, which comes above as e power x. E power x. So what I will do is I will put that e power x later, ex, ex dx. Okay, minus that minus sign and plus sign has gotten cancelled. E power minus 2x integration. There is a e power minus x above, e power minus 3x below. So I have e power x, e power 2x dx. Okay.
Yes, sir.
Now this
And
is a mere.
first, this is if we put y to the power x is equal to y, then it would be
Yes. Yeah,
easy.
we just make that substitution and then sort this
Yeah.
out quickly. So you use the substitution z is equal to e power x and dz is equal to e power x dx.
Yeah.
Okay. And what that will give me is, so in the second case, I make the substitution z equal to e power 2x and
Yes.
then dz will be 2 e power 2x dx. Okay. So first one, e minus x integration uh, e power z dz and then minus e power minus 2x uh, e power z uh, dz divided by 2, right?
Yes, sir.
Yeah. So this will be e power minus x e power z minus minus half e power minus 2x e power z. So in the first case, my z was e power x. In the second case, my z was e power 2x, right?
Yes, sir.
Yes, sir.
Right. So just check if we have made any mistakes in the calculation. Just check once.
If we put e to the power 2x equal to z in the second integration, then I
Yes,
think there
yes.
will be e to the power root z. E to the power root z method.
Just a moment. Let's do that again. Let me take like since I have just written it once, it may cause some confusion. So let me just take this part and move here, and then the second one will write a different thing. So here z is equal
So
to
we
e
can
power
also
2.
experiment with z equal to the power x.
Uh-huh. It wasn't e power z, right? It was e power root z there. So anyway, here we'll
Yes,
just
sir.
put e power x. We'll just put the same thing. What this will make it as e power z. Uh,
It
let's
is
make that
dz.
carefully. We'll write this second part carefully. Okay, e power minus 2x, e power z. Then e power 2x is z square, z square, but one of those e power x's will be taken by dz, so z dz,
Yes, so dz.
z dz, right? Now
Yes,
this is
sir.
fine. And once you do the integration, you should get e power minus 2x, and inside what you get, you will get e power
That
z,
my
z minus 1,
yes, sir.
okay? And then let's just handle this e power x, e power x, okay?
Yes, sir. That
So now this should be fine. So now let's just collect the terms. There is a e power minus x, e power x. There is a e power minus 2x, e power x. So that will have the same e power minus x outside. That will cancel. And the remaining term is this minus and inside minus will cancel. So plus e power minus 2x, ex. And as you see,
Yes.
this option exists in this world. That is, I believe, option B. So this is the option. E power minus 2x and e power x at the end.
Yes, clear.
Now this is clear.
Yeah.
Okay. Okay. So let me. Okay. So now the everyone is comfortable with method of variation of parameters.
Yes, sir.
yes, sir.
If there are like anyone else wants to ask something, please ask right away. All right. So if there seem to be no questions at this point, then let me briefly mention the operator method. In some instances, it may offer a faster way of solving a given differential equation in constant coefficients. In others, it may not. So, let me use a different- okay. So, for this, let me have the differential equation y double dash plus py dash plus qy equal to rx. This well, I will just call it as I now. It may have had a different symbol before, but let's just keep a new symbol for the time being. Okay. So here it is essentially d by dx acting on d by dx acting on y plus p time d by dx acting on y plus qy equal to rx, right? So the operator d by dx is denoted by d, okay? And then a double application of this operator d is corresponding to the second order derivative. N-fold operation is nth order derivative, and so on. So this can be written in the form d square y plus p dy plus qy equal to rx. Okay, so we can actually combine all the operators together. We can actually write this as a polynomial of operators. Okay, so if you see this q times y, there is the usual multiplication operator, but then we can think of the operator which I'm going to denote by 1 in this way, which would act like 1 acting on y giving y, just the straightforward definition. And then
Hmm.
I would
Like
have,
identity, like
yes,
identity.
identity, exactly, identity. So you can actually make combine the operators to have a polynomial of operators. T square plus PD plus QI or Q1 acting on Y equal to Rx. All right. And then the polynomial can be factorized, and then you have to do some things. So for operators, let me show you something. Let's do a first order expression. Okay, for simplicity. Let me look at dy plus py equal to gx. Okay, so this is d plus p y equal to gx. So if I have to talk in terms of operators, I would have y is equal to the operator 1 over d plus p acting on gx, right? But then I
Yes,
also
sir.
know that this dy plus py equal to gx has a solution of the form y equal to y naught plus e power integral uh, there is an integral outside uh, e power px gx dx, right?
Yes, sir.
Yeah, so this is the standard formula for that. That inside that is e power integral function of x dx type, but that function is just a constant here. So that p just becomes px. All right. So this is the form that it takes. Had it been, and then outside there is something. Outside there is something else remaining. What is that? So let me just check the correctness of what I am doing. Yeah, there is a e power minus px outside. That is what was missing. Yeah. So that we have this solution. So this y naught corresponds to, like, it will come from the integration constants and so on. So we will not worry about that, why not too much at this point. But what is more interesting is that this particular expression is being involved. So we make a definition of the integral operator, or like inverse differential operator. So 1 over d plus p acting on g, so g is a function, that will look like, so there is a plus p here, right? So you do e power minus px, so this acting on gx, equal to e power minus px integral e power px dx gx dx. Okay. So had this p been equal to 0, then you just have dy equal to gx and then y equal to integral gx dx. So this all checks out. Okay.
Yes.
Now let's go back to the second order or even higher order cases. Okay. So back to second order. I had d square plus pd plus q identity acting on y equal to rx. Okay. So assume that R1 and R2 are the roots of this auxiliary polynomial. So R square plus PR plus Q equal to 0. Okay. So which just means that I can write this as R minus R1, R minus R2. Okay. In this case, my solution y will end up being 1 over d minus R1, d minus R2, Rx, correct? If we are just treating
Yes.
the operator polynomial just the way it is. So let me add a page and drag this down. Okay. So again, there are a few different methods of going about this, and that will depend on the form of Rx. All right. So one method here. Okay, Pooja has a question. So anyway, you please write that question completely. Okay, so I will answer your Pooja. I will answer your question after I'm done with this particular part. Okay. 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 So there are two methods. One method is successive integration, which which we will write y as 1 over d minus r1 times 1 over d minus r2 rx. Okay. So this can be done in whichever order, because like d minus r1 times d minus r2 is the same as d minus r2 times d minus r1, because the differential operator, well, it will commute with itself, and here there are these p and q, those are constants, so there is absolutely no issue with these. Okay, so the successive integration works exactly like this. So for like one integration, first order, you know the formula. So that formula, like that definition is here. 1 over d plus pgx is like this. So 1 over d minus r2 rx will be, so first let me write down this d minus r1, and inside becomes e power small r2x integral e power minus small r2x capital Rx dx. So this will essentially give you a new function. So this particular guy I would want to call as maybe s of x, the entire bracketed expression. And this will then become e power r1x integral e power minus r1x capital Sx dx. Okay, so if your function Rx is of a certain form, which guarantees you that this particular first integral works fine, then you this is a much easier way to go about. And then that first integral, like finding s of x, is easy, and then you can apply the second integration and so on. Okay. So I would, should we work this problem out with one of the questions that we had seen just a while back? So that would be kind of fun. So let's see which one. Yeah.
So e to the power
Huh.
e to the power x.
Oh, the same question we want to try. Sure. So uh, just a moment. Where is that question? So yeah, I have the same file open in two different locations, so I can search it like this. So okay. So our question was y double dash plus 3y dash plus 2y equal to ex. To y equal to e power x, right? So this was our question. So we want to find yp or y, huh? So this anyway, this is going to give me a particular solution anyway. Yp here also. Okay. Oh, all right. So let's convert it in our operator form. So I have d square plus 3d plus 2 times identity acting on y is equal to e power x. So this is just uh, d plus 1 d plus 2, this whole thing acting on y e power x, and therefore y y is just the particular y is going to be equal to 1 over d plus 1 d plus 2 acting on e power x. So let's do the successive integration as 1 over d plus 1 second and 1 over d plus 2 first. Okay, so 1 over d plus 1 inside 1 over d plus 2 ex, which becomes 1 over d plus 1. So we have the definition 1 over d plus p acting on some function is e power minus p outside, e power p inside, right? So e power 2x, no, no, minus outside and plus inside. Integral e power 2x, e power x dx, right?
Yes, sir.
Do the substitution. Z is equal to e power x, dz equal to e power. So you should get a z square here, right? So you use you use z is equal to e power x d z is
So we
equal
will
to
get
dx is
z
equal
into
to
the power z dz.
so you will get z dz. See, so Pooja's question was that why is there no z square? The thing is that this is a z dx. So one of those like z square had two z's involved. One of them, those z's got incorporated with dx, and that became dz. That is why that z dz was correct anyway. So let's do this. Got it, na? Let's just complete this problem then. E power minus 2x integral e power z dz, and this we have seen it just becomes e power z minus 1 inside. So there is still a 1 over d plus 1 outside, e power minus 2x. Inside is e power z minus 1, and then z is that e power x. So e power x minus 1. So this becomes, yeah, this is going to be a bit longish, but we'll wrap this particular one up. 1 t plus 1. Uh, there is e power x common, and inside I have e power minus x minus e power minus 2. Okay. Now the next part is slightly tedious, but I will keep this as an exercise because it can be done, just that it will take somewhat longer. So I will have e power minus x integral e power x e power minus x minus e power minus 2. So it is not too lengthy also. Dx. So this has already simplified a lot. This just becomes 1 minus e power minus x, then e power x. Use the same substitution, z equal to e power x and so on, and then solve. So anyway, this I will just leave as an exercise. All right.
Yes, sir, no problem.
Okay. Okay. So this is a successive integration method. There is a second method which is also kind of interesting, which is, as you guessed, you have a 1 over something, right? So I had, uh, let's say, d minus r1, d minus r2, acting on y is equal to capital Rx. This was the form we had gotten, and we had y is equal to 1 over d minus r1, d minus r2, Rx. Okay. So the moment you have something in the numerator and a product in the denominator, we use partial fractions. So you will have to break this down into a sum of individual linear factors. Okay. So this will essentially become, I'm not going to write find out the exact values of those factors, that is up to you. But you would have this as a divided by d minus r1 plus b divided by d minus r2 for appropriate values of a and b, and then acting on Rx. Okay. And this time the question is perhaps easier to solve, or maybe not, depending on the situation. But the successive integration breaks down this into a product of reciprocal linear factors, whereas partial fractions breaks it down into a sum of reciprocal linear factors. So in most general cases, this summation method is much easier. But for some others, it may not be that fun. So let's look at another problem for like another inhomogeneous problem, and this time we will use partial fractions to solve it. Okay, so let me load this problem up. Uh, okay, let me load this here, and we will use another sheet. Okay, so I have d square minus 2d y is equal to e power 2x sin x. Okay, d square minus 2d is just d times d minus 2. Okay, so I will have y is equal to 1 over d minus 2 acting on e power 2x sin x. All right. So I am going to break this down using partial fractions. Okay. So I will have something divided by d plus something divided by d minus 2. This acting on e power 2x sin x. Okay. So if you see, this turns out to be minus half and plus half. Just verify that the constants are correct. D minus 2 times this constant plus d times this constant should be equal to 1.
Yes, sir, it is.
Yes. So when you solve that, you will get those constants as minus half and plus half respectively. And then you have e power 2x sin x dx. And then this breaks down into minus half 1 over d e power 2x sin x. And then plus half of 1 over d minus 2 acting. Okay. And this will turn out to be minus half will remain, and 1 over d is just corresponds to integration e power 2x sin x dx. And then the next one half, there is a d minus 2, so I will have e power 2x e power minus 2x rx dx dx. Okay, this inside e power minus 2x e power 2x will cancel out. You are left with just integral sin x dx, which becomes minus cos x. Okay, so this part is going to give me minus e power 2x cos x. So actually there is a half also, so I will make this as minus half e power 2x cos x. And this one is sort of an iterative integral, and this I'm not going to evaluate right now, but I think you can evaluate it. So I will not worry about that now. So minus half times something, and then there is a minus half e power 2x cos x. Okay. So this kind of expression will come out. And once you complete this, you will get the exact values of those constants, which will help you solve this. So I will give you some time, and you please solve this first integration and tell me what the answer is coming, or what the answer solution for this particular integral is coming. So anyone ready with the answer for that first integral, which I just kept blank as a bracket? Essentially, I'm going to get something involving e power 2x. Inside what is there is the question. There will be some combination of sin x and cos x. So what are the appropriate constants is the question. So let me just
For
clean
the
this up.
first integration,
Yes.
for the first integration, we are getting sin x into e to the power 2x by 2
Hmm.
minus of integration cos x into e to the power 2x by 4 dx.
Okay. So just tell me e power 2x sin x dx. So the first you got half sin x
Sin x,
e
yeah,
power 2x
into e to the power 2x
minus
minus integration
hmm,
cos x into e to the power 2x by 2 dx.
so that half is still there, right? When you do the
Yes,
same
sir.
thing for cos, what do you get? So now just take this part, integral cos x e power 2x dx. So that time you are going to get another half sin x dx. Let me just do it here. So I should get, wait, e power 2 sin x had just come out, right? So cos x will come out. So integral cos x e power 2x dx will be uh, half cos x e power 2x minus integral. There will be a plus because when I take when I change sign, I will have something else. So plus uh, half again sin x e power 2x dx. Right? Will this come? For cos x e power 2x. So I got a half cos x e power 2x, that is fine, minus that half constant is still there, integral. I have done another derivative, and then I should get a sin x e power 2x. Right?
Yes, sir, that is the
Yeah,
Yes.
and the inside is a plus sign. So with this, so let me just replace this cos x by that integral cos x dx. So okay, let me add a page and then do this. So I will write this again. Integral e power 2x sin x dx equal to half sin x e power 2x minus half cos x e power 2x plus half integral e to power 2x sin x dx. Okay. So now I have integral e power 2x sin x dx here. And on the other hand, I have half sin x e power 2x minus 1 by 4 cos x e power 2x. And there was a minus 1 by 4 on this side. So that will go on the other side. And I will have a 5 by 4 here. Okay. So therefore, this thing is equal to, it will go away, 4 by 5 times 1 by 4 and minus 4 by 5, 1 by 4. So combine them properly, and I will have uh, 2, 2 by 5 sin x plus minus 1 by 5 cos x times e power 2x. So that is what goes in there. So x minus 1 by 5 cos x. And then like in the original equation, there was also minus half e power 2x cos x lurking outside. So expected solution for the problem is, let me just see. So ypx ypx is equal to, so this part I'm going to write again. So let me combine the constant, minus 1 by 5 sin x plus 1 by 10 cos x minus, there is a half cos x whole times e power 2x. Correct? So this becomes, so 1 by 10 minus 1 by 2, that is minus 2 by 5.
Minus 2 by.
So I will take minus e power 2x by 5 outside common, and inside I will have sin x plus 2 cos x. Okay. So this is a particular integral. And if you look at the solution, option C is the only one which offers that solution. It will be written in a different order. It has like 2 cos x plus sin x, and we had written it sin x plus 2 cos x. So this is correct. Okay.
Yes.
Okay. So the thing is that whether there were e power 2x sin x, whether there were some sec x or cosec x, or maybe even some other complicated function on the right hand side, the operator method as well as variation of parameter methods simply are not worried about what is there. They will just give you the solution properly. But anyway, this thing is dependent on the coefficients being constant. The coefficients being variable is an entirely different ballgame. So actually, we won't be able to cover the variable coefficients case for second order differential equation. So at this moment, I'm going to skip that. In case we are allowed another session later on, maybe then we can cover it. But if not, then you'll have to look for your own. Okay. So there is one final topic, which is a very tiny topic that I'm going to cover finally. So that is the topic of Cauchy-Euler equation or Euler-Cauchy equation, whichever way you want to say. So these equations are a special kind of second order differential equation where you will have the equation given in the form x square y double dash plus p times x y dash plus q times y equal to 0 for the homogeneous case and equal to Rx for the inhomogeneous case. Okay. The moment you have an inhomogeneous case, you can simply use variation of parameters or operator method or whichever other method that is suitable. But the thing is, look at these terms. So if anyone were to guess a form of the solution for y, compare this with the usual differential equation with constant coefficients. So compare with uh, y double dash plus, I will just write capital P and capital Q for the constant coefficients for the time being, plus Q y equal to 0. Okay. So in the usual constant coefficients case, we we made use of the one variable case where a derivative just being the original function just appropriately scaled corresponded to exponential function. In this case, if you see that there is a like power of x attached to the derivative of y. Okay. So if my derivative is first order, I have attached an x. If the derivative is second order, there is a x square attached. You can have it as the higher order case as well, where you will have x power n nth derivative of y plus something x power n minus 1 nth derivative of y and so n minus 1th derivative of y and then so on. So such a thing, if you think about it, is essentially keeping the degree same throughout. Okay. So here the guess solution is y is equal to some e power rx, which gave us the auxiliary polynomial r square plus pr plus q equal to 0, and which we solved. And then the solutions gave us y homogeneous equal to c1 e power r1x plus c2 e power r2x, right? r2x. In the Cauchy-Euler equation case, we are actually going to see like that the degree is kind of being preserved. So y equal to x power r might be a better idea instead of y being e power kx or e power rx. So we use our guess solution. So y is equal to x power r. Y is equal to e power rx. Okay. And then correspondingly, if I substitute y equal to x power r, I have y dash is equal to r x r minus 1, y double dash is r minus 1, x r minus 2. Okay. You make that substitution, you get r minus 1 x power r, because there is an x power r minus 2 and there is an x square, plus p uh, r x power r plus q x power r equal to 0. Now x power r is common, and such equations always necessarily have x strictly greater than 0. So you can actually divide throughout by x power r, and then you get the form for auxiliary equation as r minus 1 plus pr plus q equal to 0, and which is r square plus p minus 1 r plus q equal to 0. Okay. So compare it with the usual differential equation with constant coefficient. There is r square plus pr plus q. Here it is r square plus p minus 1 r plus q. Okay. So there is that tiny change that one has to keep in mind. Okay. So anyway, what are the solutions for this? Like auxiliary equation, r plus minus is equal to 1 minus p plus or minus p minus 1 square minus 4q divided by 2. Yes. And then correspondingly, my y homogeneous would be of the form C1 x power r plus C2 x power r minus. All right. So this again has its own interesting things. So let's look at a couple of problems and then we will close the session actually. So let me pick a problem for you. So this particular problem will actually combine something that we have done just a little while back with this Cauchy-Euler equations. So let's get the question. All right. Okay. So as you can see, this is a Cauchy-Euler equation where the auxiliary equation is. So here notice that my p is equal to -2 -4. Okay. So what I have is r square plus p minus 1 r plus q equal to 0. So this is r square minus 3 r minus 4 equal to 0, which readily factorizes into r plus 1 r minus 4 equal to 0. Okay. R equal to -1, R equal to 4. These are the solutions. Okay. And therefore, my linearly independent solutions are y1 is equal to x power -1 and y2 is equal to x power 4. And a linear combination of these is going to be your homogeneous solution. Okay. But I just kept the linearly independent solutions because the question is actually talking about Wronskian. Okay. So let's just see. Y1 dash is equal to -1 over x square and y2 dash is equal to 4x cube. Right. So what is my W? W, as the formula suggests, is y1 y2 dash minus y2 y1 dash, which turns out to be 4x square plus x square, right, equal to x power 5x square. Okay. So this is my Wronskian. Not really put any constants there, right? So let us put constant C1, C2, there will be corresponding C1, C2, C1, C2 peppered throughout. So my effective answer is going to be 4. So let's just put those. There is C1 over x square and then 4C2 x cube. So C1, C2, here C2, C1. So this effectively becomes 5 C1, C2 x square. Okay. This is fine now. I have just introduced some constants because I have to evaluate the Wronskian according. So we have W1 equal to 1. Okay. So that 5C1, C2 equal to 1. C1, C2 equal to 1 over 5. Then if I do W3 minus W2, that is going to be equal to 5 C1 C2 times 9 minus 5 C1 C2 times 4. That is equal to 5 times 5 C1 C2. So actually we did not even need to evaluate that C1 C2 or something. We could have simply gone straight from Wx. We did not need to even evaluate it. Okay. So anyway, so so this was W1. So since W1 is 1 and I got 5 times W1, my answer is 5. Okay.
Yes, sir.
Yes. All right. So I think we will have to stop here, and then maybe I will find out with the organizers whether we can have some extra sessions later on, but definitely not next week. All right. So let's stop here. Uh, Back to you, Prathamesh sir.
Sir,
Yes.
sir, if the order of differential equation more than 2, then the Euler-Cauchy equation is different from this one. Yeah.
Obviously. So that time you will still make the substitution or guess the solution as y equal to x power r, and then your third derivative is going to be what? R minus 1 r minus 2 times x power r minus 3, right? So make
Yes,
that
sir.
substitution. You will get the appropriate auxiliary equation. So you will have r minus 1 r minus 2 plus whatever the first coefficient times r minus 1 plus second coefficient times r plus third coefficient equal to 0 as a cubic. Okay. And once you equate the coefficients properly, you will get a different cubic as an auxiliary equation. And then from that you can follow.
Okay, sir.
Yes.
Sir, what if the power of hello?
Yes. Go ahead.
Yes, sir. So what if the power of x and the order of the derivative are not same? Then how we will do the solution?
See, they don't need to be the same. You are just putting some like guess x power r. So if you have more orders, more derivatives, you do them, combine them, you will get a different solution. So let me just write it on a. Okay, there is some space here. So let me just write about this. So the substitution is just y is equal to x power r, right? So if I have a degree 3 situation, for instance, I have some x cube y triple dash plus px p. Instead of p, let me write capital A, capital B, capital C as my coefficients. Okay, ax square y double dash plus bx y dash plus c y equal to 0. This time I'm going to have make the substitution and have r minus 1, r minus 2. Let me just write this down. Plus a r minus 1 plus b r plus c equal to 0. Equate this and you will get some r cube plus a tilde r square plus b tilde r plus c tilde equal to 0. These a tilde, b tilde and c tilde, they will come from the appropriate coefficients from here. Okay. So that was Akash's question. Now this second question, could you repeat that?
Yes, sir. If the power of x and the order of derivative are not same, such as if there is x to the power 4, y triple dash, something like that.
So you have to see if the total degree is the same for each term. You could potentially have something of the form xy double dash plus maybe some a times y dash plus b divided by x y equal to 0. This kind of situation is also possible. But then there is an underlying condition of x strictly greater than 0. So you are actually allowed to multiply throughout by x so that your degrees are matching. And you will get x square y double dash plus a x y dash plus b y equal to 0. Then it gets to a standard form and you can solve it.
Will we always be able to convert it into the standard form? Or
Typically, you can. Of course, if you have some other kind of terms, for instance, maybe some x square plus 1 y double dash plus a x minus 1 y dash plus some by equal to 0. So this is no longer an Euler-Cauchy equation because you are having some cross terms. So for these you will have to resort to a different method, which I'm afraid we do not have time for today.
okay, sir.
Yeah. So I will just mention some methods, some extra methods which can potentially be used. So there is something called reduction of order. Okay, which essentially works like this. So there is a known solution. Let's say y1 is the known solution. And then you want to find a linearly independent solution y2. So that particular reduction of order method does find y2 is equal to v times y1, where v is another function. And if the differential equation is of the form y double dash plus px y dash plus qx equal to rx. Let's forget about the rx part at that this time and put it at 0. I have this px. So your effective form of v will become some 1 over y1 square. That y1 is a known solution. And then e power minus integral px dx dx. Something like that. Of course, since we do not have that much of time, I won't be able to properly describe with examples and so on. We have to wrap up. I have been just instructed by our organizers that we have to stop. So we won't be able to cover that.
Okay, sir.
Okay. Okay, if there are no further questions, I think let's make a wrap now. We'll stop for today.
So do you want to give us some advice for preparation?
Yes. So the thing is, be it a question on like questions on ordinary differential equations or linear algebra, abstract algebra, or whichever. The thing is, in for this particular exam, you need to have a perfect time management. There will be a bunch of questions which will be rather easy to solve, and you absolutely 100% are certain that you are going to solve them in less than a minute or something. Go ahead and simply solve them, mark them, and don't think about them much. Those which are kind of difficult, you maybe spend 1.5 minutes or maybe 2 minutes, not more than that, and then see whether you can get a solution. So sometimes you will simply remember what you have studied, you will utilize that. But otherwise, if the time is kind of running low, you will just revisit that question a bit later. Maybe try elimination of options. Maybe try some other method and get the solution, and so on. Time management and keeping calm are the two crucial things in like these all of these exams. Now about the actual like material, there are like specific books. I'm not talking about like problem banks, question banks, or previous year question papers or such. There are certain really nice books that will actually help. So, for instance, I will show you a particular book which I have. So, let me just temporarily stop sharing my screen and so that my face is visible. So, I have this particular book. Okay, let me. Okay, I don't know whether I can remove. Okay, let me just remove the background effect and show you a book. Okay, differential equations with applications and historical notes. The book is by G.F. Simmons. Okay. Yeah. So this is a very nice book, and like this gives you a lot of different like easy problems and methods to solve. Okay. So that is one book. There are several other books that you can see which will have nice problems. So, for instance, there is a book on differential equations and initial value problems, initial and boundary value problems by Boyce and Diprim. That will also give a lot of like nice, so like a huge number of problems and methods and solutions, techniques and so on. There is also another book, Kreyszig's ordinary differential equation, not the engineering mathematics one. So that book will also have a lot of nice problems that you can practice. The thing is that there are like small things, small specific like techniques. So you have to make these like understand these techniques very well and have a slight pattern recognition idea. So when you see a problem, suddenly that specific pattern will click and you will be able to solve that particular question. But unless your basics are absolutely sound, you won't be able to do anything in many of these exams. So make these basics like really, really precise. I think that's the only general uh, advice that I would like to give to everyone.
Sir, can you repeat the book name of?
Okay, so I will just tell you the names of the authors. I think that will be rather easy to follow. So the one of the easiest books is by George F. Simmons, G.F. Simmons. That is differential equations with applications and historical notes. Then there is another book, Introduction to Differential Equations and Boundary Value Problems by Boyce and Diprima, Boyce and Di Prima, Prima. And then there is the third book by crazy, but on ordinary differential equations. Okay. So Charu also had a question, but I believe I already answered that in the pages.
I hope there are no more queries left. Gaurav Sawant sir, we are deeply grateful for your presence. We appreciate the time you took to share your knowledge with us. Thank you for your valuable contribution to this lecture series, sir,
Yes.
through your four wonderful sessions. We
Thank you.
are honored to have you with us, sir, and we look forward more such sessions with you, sir.
Yes. Thanks a lot to.
Yeah.
Okay. Thank you, organizers, for the kind words. So anyone, if they want to say something, they can say.
Thank you once again, sir.
Thank you. Thank you, everyone.
Participants, we have shared a feedback form link for Gaurav Sawant sir's session in the chat box. I request you all to kindly give your valuable feedback. Also, please note that next session will be on tomorrow, that is on Monday, 22nd September 2025, from 7:30 p.m. to 8:30 p.m. as per the change schedule. Let us meet there. Goodbye.
Okay. Goodbye, everyone. For now, all the best.
Good night, sir. Thank you, sir.
Yes.